Okay, this is lesson 24 of Module 4, 8th grade math, and we are going to continue talking about linear equations, but this time we're going to be talking about something called simultaneous equations, and simultaneous means at the same time. So these are situations where more than one equation is required. So we'll have either two or more equations that will be solved at the same time or simultaneously. This is also called a system of equations. So let's just dive right into the first exercise. So it's this is basketball, and Derek scored 30 points in the game and didn't go to the free throw line at all. So that means all of his shots were 2-point or 3-point shots. So we're going to list as many combinations of 2-point and 3-point shots as we can that total up to 30. So I'll get you started. So we could have 15 2-pointers and 0 3-pointers, and that would be 30 points in all. 15 times 2 is 30. So go ahead and pause the video and think of some more combinations that would add up to 30 points that Derek could have made. Okay. Okay, so let's look at the rest of the data. So we could have 0 2-pointers and 10 3-pointers, and that would be 30. 9 and 4, 12 and 2, 6 and 6, and 3 and 8 are some of the other combinations that you might have found. All right, so if we wanted to write an equation that described this data, we would need to first define our variables. What are our variables? And so let's think about that for a minute. Okay, so the thing that can change in this situation is that we can have a different number of 2-pointers and 3-pointers. So it kind of makes sense that we could let X be the number of 2-point shots and Y be the number of 3-point shots. Okay, and if that is how we define our variables, then let's think about how we would write an equation to describe the data, to describe what is going on with these, the sum of these 2-pointers and 3-pointers adding up to 30. So if you think about how you figured out what would be, I have to fix that. What would the total score be for any one of these? You took the number of 2-pointers and multiplied it by 2, and then took the number of 3-pointers, multiplied it by 3, and then added it together. So that would look like this. We would have 2 times the number of 2-pointers, or 2 times X. Add that to 3 times Y, and we want that to equal 30. So there is the equation that would describe this data right here. So, and we can see that there are several possibilities for solutions to this equation. Okay? All right, so let's look at exercise 2 now. Okay, so in exercise 2, it says that Derek now tells you that the number of 2-point shots that he made is 5 more than the number of 3-point shots. How many combinations can you come up with that fit this scenario? And it says don't worry about the total number of points. So if all we know is that the number of 2-point shots has to be 5 more than the number of 3-point shots, here is a combination that works. We could have 5 2-pointers and 0 3-pointers. And we can keep going along here and see there's other combinations that would work too. We could have 6 and 1, 7 and 2, 8 and 3, as long as the number of 2-pointers is 5 more than the number of 3-pointers. Okay, so now we're asked to write an equation that describes this data, that the number of 2-pointers is 5 more than the number of 3-pointers. So you might want to pause and try to write that equation yourself first, and then come back. Okay, so we could write something like this, that y plus 5, and remember y is the number of 3-point shots, so the number of 3-point shots plus 5 is equal to x. You may have written it this way, that I could look at the number of 2-point shots, subtract 5, and that would give me y. So these are equivalent equations, because if I take this 5 and add it to both sides, I end up with this equation right here. So they're the same. They're the same equation. Okay, so now we're asked in exercise 3, which pair of numbers from your table in exercise 2 would show Derek's actual score of 30 points. So look at your 2 data tables and see if you can find a combination that fits this rule on this table and also gives us 30 points. Okay, so you might have noticed that 9 times 2 is 18, and that if I take 4 times 3 to get the number of 3-pointers, that's 12, and 18 plus 12 is 30. So 9, 4 was one of the combinations we found on the first data table. So 9, 4 right here is a solution to that first equation. Okay, so this problem is an example of simultaneous linear equations. When we had just one equation at a time, there were multiple solutions for them. But when we put them together, we found one. And so this is also known as a system of linear equations. And here is our system of linear equations. We had 2x plus 3y equals 30. This was the rule that the number of 2-pointers plus the number of 3-pointers had to add up to 30. And then also that the number of 2-pointers was 5 more than the number of 3-pointers. And so we use this notation with the brackets next to the 2 equations to show that we're talking about a system of linear equations, not linear equations independently. And so we're going to get a different solution because the solution has to satisfy both equations. So over the next several lessons, we're going to look at different methods for solving a system of linear equations. You just solved one by making tables and just figuring out what combinations of x and y would work for both of these equations. In this lesson, we're going to use graphing to solve. So what I want you to do is get a piece of graph paper and see if you can graph both of those equations, both of these equations right here, on one coordinate grid. And just make sure you label them by which line you're plotting. It shouldn't be too hard to do this because you have data points already. So these are data points for y plus 5 equals x, and right here these are data points for 2x plus 3y equals 30. So if you just plot a couple of these points and connect the line, and then a couple of these points, whichever ones you choose, and connect the line, you'll have your graph. Okay, and we want to to see what the graph looks like and what information we can get from it. So go ahead and pause now and work on that graph and see if you can tell something about it. Okay, so this graph, I'm going to start putting some points on, and so I could ask you which of those equations do you think this graph is? And then, so this line you might realize is the y plus 5 equals x line. And there's some points from the other equation. I connect those and let's label them. So the purple line is the 2x plus 3y equals 30, and the green line is x equals 5 plus y. So you might notice that their point of intersection is actually where x equals 9 and y equals 4. And if you'll remember, that was what we decided was the solution to both of those rules or situations there. So this shows that you can solve a system of equations by graphing. Now, some graphs aren't going to be right at grid lines and come out this nicely. And so there are other methods besides graphing for solving these simultaneous linear equations. So like I said, in this lesson, we're just going to use graphing, but in lessons to come, we're going to use more algebraic methods. Okay. Okay, one more thing that I could say about this is that just like linear equations in one variable, we looked at situations where there was one solution, no solution, or infinitely many solutions. And that's going to be the case with simultaneous linear equations also. This pair of linear equations has one solution, and it's the point that is on both of those lines. And it's pretty intuitive here that there's not going to be another solution, that this is the only solution in this case. But once again, sometimes there can be no solution, and sometimes there might be infinitely many. So we'll be looking at that in later lessons. Okay, we're going to look at an example now. We're going to look at example 1, which you do not have in your notes, but I've sent a copy of some notes of this, but you can just follow along on the video as well. So, okay, so here we go. Example 1. Pia types at a constant rate of 3 pages every 15 minutes. Suppose she types y pages in x minutes. Pia's constant rate can be expressed as the linear equation 1/5 x. Y equals 1/5 x. Okay, so let's pause the video and think about why that is the equation for Pia's typing rate. Okay, so we are working with a constant rate problem. So we know that if we take our y pages in x minutes, that is a constant rate and that it's going to be equal to her rate that's given here in the problem, which is 3 pages every 15 minutes. Okay, and if we want to multiply both sides of this equation then by y, we would get that y is equal to 3/15 times x. Sorry, we didn't multiply by y, we multiplied by x. So let's get rid of that. Sorry. Okay, so we got x here and x here. Hopefully you caught my error there. We did that so that the x's would, x over x is 1, so the x's would cancel. And we're left with y equals 3/15 x, but we should notice that 3/15 simplifies to 1/5. So in other words, if she can do 3 pages in 15 minutes, she can do 1 page in 5 minutes. And so here's her, on this data table, here's some points, basically, some combinations. So in 5 minutes, she would do 1 page. In 10 minutes, 2 pages, and so on. All right, so here's the graph of y equals 1/5 x. And so if she were just typing, we could see at 0 minutes she would have typed 0. And if we come over here to 5 minutes, she would have typed 1 page. And if we could follow this out to 10, she would have typed 2 pages. So this is the graph of Pia's typing. Okay, but look with me at the bottom of the page here. It says Pia typically begins work at 8 a.m. every day. On our graph, her start time is reflected as the origin of the graph at 0, 0. So this would be 8 a.m. right here. So really this part of the graph doesn't really matter that much, but it is part of the line. So that would be 0 minutes worked and 0 pages typed. For some reason, she started working 5 minutes earlier today. How can we reflect the extra 5 minutes that she worked on our graph? All right, so think about what the graph would look like with Pia starting 5 minutes early. Okay, so her rate is the same. Her rate is the same at 1 page every 5 minutes. But if she started 5 minutes early at 8 o'clock, which is 0 on the x-axis, at 8 o'clock, she would have already typed 1 page. If you think about it, she'd already been working for 5 minutes, so she would have typed 1 page. So we can actually put a dot there on the graph. Okay, so that point for x equals 0 right here, y equals 1, shows that at 8 o'clock she had a head start. She had already typed 1 page. So let's go ahead and put one more point on this graph. So after 5 minutes at work, she hadn't typed just 1 page, but she had typed 2. So we could put another point there. And then we can draw our line through that. So that would be representing her starting 5 minutes early. So you might notice that these lines are parallel. That's because her rate is the same no matter what time she starts. And so what would the equation of this line be? So if you want to think about that, pause the video. And see if you can write the equation for that line. You should be able to. Okay, we know the y-intercept and the slope of this line. And so the equation of this line is y equals 1/5 x plus 1. So the slope is 1/5 and the y-intercept is 1, showing that she already had some work done when work started. Okay, there's another way we could write this equation, and that looks like this, that y is equal to 1/5 times x plus 5. And so this is really just factoring a 1/5 out of the rest of this equation. And you'll notice that if you use the distributive property, you go from this equation to this equation, because 1/5 times 5 is 1, and you'd have 1/5 x. Okay, and if we extend this line all the way back along the x-axis, you notice that when y is 0, x is -5. So what that's showing is that she started work at 5 minutes before her regular time and got a certain amount done. So she's going to be ahead like that all day. Okay, so the reason we're showing you this example is because most of the examples and the problems in the problem set have to do with rate, like a speed, where somebody starts early or somebody gives somebody else a head start and that sort of thing. So we need to know how to adjust the time. And so let's notice this worked fine. We figured out how much work she would have had done by her regular start time of 8 o'clock, and we were able to write the equation that way. But if you look here, the extra 5 minutes is a little easier to see. Her time, she has plus 5 minutes. And so the equation in this format really highlights the fact that she started 5 minutes early. This one's kind of hiding that fact a little bit. So there's nothing wrong with this equation, but this one really shows the 5 minutes there. Okay, so let's look at one of our other examples now. Okay, so example 3 is another one that I printed up on that double-sided notes page. We're skipping example 2, so you didn't miss anything. And so this one, like I told you, is going to be about speed, about running rate. Actually, this one's biking. So let's just look at it. Randy and Craig ride bikes at a constant speed. It takes Randy 25 minutes to bike 4 miles, and Craig takes 32 minutes to bike the 4 miles. If Randy gives Craig a 20-minute head start, how long will it take Randy to catch up? Okay, so we are asked to find and write linear equations to match each person's bike ride motion. Okay, so we've got Randy and Craig, and we want to take into account their speed. So we're going to have a couple variables here. So we're going to have x stand for time and y stand for distance. And remember, I mentioned before that the fact that x stands for time is kind of universal. We like time to be on the horizontal axis, usually, not always, but usually. And then the vertical axis is for the distance traveled. Okay, so that's going to be our y variable. Okay, so let's look at Randy and Craig here. And we have, remember, we have a constant rate. So we can say that y over x is equal to 4 over 25. So he goes 4 miles in 25 minutes. And that's ratio is always going to be the same. So when Randy goes y miles in x minutes, then we have this equation. So multiplying both sides of that by x, I get a new equation that says that y is equal to 4/25 times x. Okay, so the distance equals the rate times the time. Distance equals rate times time. And that's another way to think of that equation. Okay, so Randy's just going at 0 minutes. He's heading out, not taking a head start. But Craig is taking a head start. And so, why did that go over that? So we have that Craig can go 4 miles in 32 minutes, And we can simplify that down to 1 mile every 8 minutes. And this would be our equation for Craig. So notice that when x equals 0, we put 0 in here, then y is still going to have a value. It's not going to be 0. Whereas in this equation over here, which I need to fix, my technology is having a mind of its own. So that was y is equal to 4/25 times x. When x is 0 over here, Randy's distance will be 0 because anything times 0 is 0, so that will be 0. But over here, notice that Craig at times 0, when Randy starts, has already been riding for 20 minutes. So his time is not just x, it's x plus 20. And another way to write this equation would be y equals 1/8 x plus 5/2. And that's using the distributive property. 1/8 times x is 1/8 x. And 1/8 times 20 is 5/2 or 2.5. Okay, so this 5/2 represents that amount of traveling that he can do in his 20-minute head start. So in 20 minutes, he could go 2.5 miles. In class, somebody brought this up and talked about it like this, that if he can go 1 mile in 8 minutes, then I want to know that would be equal to how many miles in 20 minutes. And we thought through it kind of this way. In 16 minutes, he would go 2 miles. So we need another 4 minutes to make it to 20. And in 4 minutes, he could go half a mile, because in 8 minutes he goes 1. So in half of that time, he could go half the distance. And so in 20 minutes, he could go 2.5 miles. So that's where that comes from in that equation. Okay, so now we're going to look at the graph for Craig and Randy. And this is what those equations graphed look like. So notice that, and see the notes here, think about the y-intercepts and what those points are standing for. So on Randy's y-intercept is 0, but Craig's y-intercept is just above the 2 mark. And so you can see that at 0 minutes, Randy had gone 0 miles. But at what we're calling 0 minutes, Craig had already been traveling for 20 minutes. So this x equals -20, this x-intercept here shows actually when Craig started. So he'd been traveling 20 minutes. And remember, we said he could go 2.5 miles in that 20 minutes. And that's what his y-intercept looks like. Okay, and then they both travel on. So now we can, because we've adjusted Craig's time and Craig's graph to match up with Randy's times, then we can look at this. And so our question is, how long will it take Randy to catch up with Craig? So how can our graph help us decide that? Okay, so when Randy catches up with Craig, that means that the miles that they've traveled will have been the same. So here, Craig is 2.5 miles ahead of Randy. And so as they travel along, the point where these two lines intersect is the place where the distance that they've traveled is the same. And so we can look at that. So let's look at where that is. So if we draw down to the x-axis right here, draw a line straight down, we'll see that that's at about 70 minutes. And then over to the y-axis, I drew it kind of a little wonky, but it would be at about 11 miles. So 11 miles into this bike trip is when they're going to meet up. And if they keep going at their constant rates, Randy's going to end up pulling out in front and Craig will be then behind. Okay? Okay, so this was a system of linear equations or simultaneous linear equations. And once again, we found on the graph, we found the point of intersection, and we said this is the point that satisfies both equations. And so it's the solution to our question, okay? And so here we can see the 70 minutes and 11 miles. So this 70 minutes is the time that Randy has been traveling, but notice Craig has actually been traveling for 90 minutes when we get to this point on the graph. Okay, so there's a lot we can tell from a graph that helps us to come ballpark. Now, it's not exactly 70 minutes. We can't tell that from this graph, and probably not exactly 11 miles. But we can get close. And remember, we talked about how we're going to come up with other methods for solving these systems of linear equations that will give us a more exact answer. But for now, this is fine. Okay, now let's look at exercise 4, and this one you have in your classwork notes. Okay, so exercise 4 says Efren and Fernie are on a road trip. Each of them drives at a constant speed. Efren is a safe driver and travels 45 miles per hour for the entire trip. Fernie is not such a safe driver. He drives 70 miles per hour throughout the trip. Fernie and Efren left from the same location, but Efren left at 8 a.m. and Fernie left at 11 a.m. Assuming they take the same route, will Fernie ever catch up to Efren? If so, approximately when? So write the linear equation that represents Efren's constant speed and make sure to include in your equation the extra time that he was able to travel. And then in part B, we'll write the linear equation that represents Fernie's constant speed. Okay, so pause the video and see if you can get those equations going. And then come back and we'll go over it together. Okay, so Efren travels 45 miles per hour. So we could think of his equation being y equals 45 times x. Because at this speed, you think about it, this is distance equals rate times time. These are the ones that we also write as the ratios of the constant rates, and then we do some algebra to solve them and get them in this form. But I think this one's pretty clear that y is equal to 45x. But notice we have to adjust this equation because Efren is leaving 3 hours before Fernie. So he's got an extra 3 hours to travel. So we could show that a couple ways. One way is to show that he has 3 extra hours. So his time is the time plus 3. The other way you could think of that is to figure out how far would he have gone in those 3 hours before Fernie leaves at 11. And I know that 3 times, if he traveled for 3 hours at 45 miles an hour, he would already be at 135 miles by the time Fernie leaves starts on the trip. Okay, so, but notice these two equations are equivalent because if I multiply out these parentheses, I'd get 45 times x plus 45 times 3, which is my 135. Okay, so the linear equation that represents Fernie's constant speed is just distance equals rate, 70 miles per hour, times time, which we're using x for. Okay, so part C asks us to write the system of linear equations that represents the situation. So here it is. So don't forget to use the brackets. The brackets show that these equations have to be solved at the same time or simultaneously. So just put the brackets around a system of equations. We've got two equations here, and we're going to sketch the graph of these equations to help us figure out when Fernie is going to catch up. Okay, so we're going to call time 0 when Fernie takes off on the trip and Ephraim's already been traveling. So we're going to, at 0, when x is 0, y is going to be 135 because he would already have traveled that. So let's think about at 2 hours, he would have gone another 90 miles. So 90, 100 and, let me do it over here, 130, okay, 135 plus another 90 miles would give us 225. So at 2 hours, he would have traveled 225. So let me find that point. 2 hours would be 225. So right about there. Okay, so we'll connect the line to see Ephraim's travels. Okay, so that's what Ephraim's graph looks like. So that would be the first one right here. Oh, wrong tool. Okay, so that's y equals 45x plus 35. So let's graph Fernie's graph now. So Fernie at time 0 is still is just getting ready to go. And so let's think about this. If in 2 hours he would go 140 miles. So let's find that. So in 2 hours, just shy of 150. So there is, there are 2 points for Ephraim. Okay, and then we could do even one more at 5 points. At 5 hours, hours, he's going to have gone 350 miles. So let's see if we can get that on there. 5 and 350. So the two lines look something like this. And so let's tackle the questions now. E, will Fernie ever catch up with Ephraim? If so, approximately when? So this is the point where their distances are equal. So this is going to be our clue to when Fernie caught up with Ephraim. And we're also asked at approximately what point do the graphs of the lines intersect? So we'll look at that now as well. So it looks like from the graph, if we follow the point of intersection down, that it's at about 5 hours. So at about 5 hours and about 350 miles is when approximately Fernie will catch up to Ephraim. And so the time, if it's 5 hours from 11 o'clock, then the time would be about 6 p.m. that he would catch up. And so Fernie will have been traveling for an extra 3 hours at that point. And but the time will be about 6 p.m. And so the lines intersect at approximately 5:3:50, somewhere around there. Not exactly, but close enough for our graph. So after about 5 hours of traveling, Fernie will catch up with Ephraim. Okay, let's look at one more example and then you'll be ready for the problem set. So in this example, Jessica and Carl run at constant speeds. Jessica can run 3 miles in 15 minutes and Carl can run 2 miles in 8 minutes. They decide to race each other. As soon as the race begins, Carl realizes that he did not tie his shoes properly and takes 1 minute to fix them. So we are going to start by writing the linear equation that represents Jessica's constant speed, and we'll include in her equation the extra time that she was able to run. And then we'll write a linear equation for Carl and a system that represents the situation. And then we'll be graphing it to find an approximate solution. Okay, so let's start with Jessica in part A. So her rate is 3 miles in 15 minutes. And it's always good to simplify that if you can. So if she goes 3 miles in 15 minutes, she can go 1 mile in 5 minutes. And so since that's a constant rate, we know she can go y miles in x minutes. And so this equation becomes y is equal to 1/5 times x. All right, but remember that she is getting a 1 minute head start because Carl has to fix his shoes. So we're going to call this 1/5 times x plus 1. So she was traveling an extra minute when Carl started. Okay, and so then the linear equation that represents Carl's constant speed would be his rate, which is 2 miles in 8 minutes, which is the same thing as 1 mile in 4 minutes. So Carl's equation would be y is equal to 1/4 times x, the time. So he goes 1 mile every 4 minutes. Okay, so distance equals rate times time. Okay, so we're going to write a system of linear equations that represents this situation. And so we're going to use our notation here. So we have y equals 1/4 x. And then I'm going to rewrite this equation a little bit. I'm going to write this as y equals 1/5 x plus 1/5. Okay, so remember this extra 1/5 is that extra distance that Jessica could go in the minute that Carl wasn't running and was tying his shoe. Okay, so there are our equations, and so what we want to do now is graph them to find an approximate solution. Okay, so notice the scale on this graph. The y-axis is 0, 2/10, 4/10, and so on. and then the x-axis is still 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so we are miles per minute. So on the y-axis, this is, of course, miles here and minutes here. Okay, so let's get a couple points on here. So for Carl's graph, let's write the equations first. So here is the system of equations up here. And let's go ahead and get a couple points on the graph. So first, for Carl's graph, he has points at 0, 0. And then his is y equals 1/4 x. So in 4 minutes, he will have gone 1 mile. Right there. In 2 minutes, he will have gone a 1/2 mile. So that will be between 0.4 and 0.6. So right about there. Okay, so there's the line for y equals 1/4 x, and it's right here. So now I need to graph y equals 1/5 x plus 1/5. So when x is 0, that would be a good point to graph. When x is 0, y is 1/5. And so we're going to get our circle tool and put that on here. So 1/5 is 2/10. And so we can mark that right on our graph. And then we can pick another point. We could pick 5 as our point. So at 5 minutes, we are going to have 1/5 times 5, which is 1. And then plus 1/5, which is 1.2, or 1 1/5, 1.2. So that point on our graph is at 5, 1.2. Okay, so that lies below the line a little bit, but let's go ahead and connect the dots on this one. So here's Jessica's line. Or is it Jessica? Yes. Carl and Jessica. Okay, so Jessica's line is this one over here, and it is y equals 1/5 x plus 1/5. Okay, and so when we look at the intersection of these two lines, we notice it right here, and it's actually on a grid line. It's the point 4 minutes past this start time here. 4 minutes past Carl's actual start time, not when he started tying his shoes. Okay, so that would be, let's look at this, the solution to this. That would be at 4 minutes and 1 mile. So this is somebody who traveled or rather someone who was at the 1 mile point in 4 minutes. Okay, so let's keep this graph and let's go look at the questions that were asked about it. So use the graph to answer the questions below. If Jessica and Carl raced for 2 miles, who would win? Explain. So if they raced for 2 miles, 2 miles would be right up here. And if I carry it over, you'll notice that this is Carl's line. And so if we want to extend, I'm going to use green to do it. if we want to extend Jessica's line, it's going to come out here somewhere. So at 2 miles, Carl would win if that was the ending point. Carl would be the winner even though he had to stop for a minute and tie his shoe. Okay, so we found that out by following this at 2 miles is on the y-axis all the way over to the graph. And we notice that in 8 minutes is when Carl finished, and then we have to come all the way over here to about 9 minutes to see when Jessica made it to the 2 mile mark. Okay, so Carl would win, and it's because they had gone long enough for Carl to catch up and then go past Jessica. Okay, so if the winner of the race was the person who got to a distance of half a mile first, who would the winner be? All right, so once again, we're going to come over here on the y-axis and look for half a mile, and it's right in here between 0.4 and 0.6. So at half a mile, notice that Jessica gets there in about 1.5 minutes from this start time. And Carl doesn't get there until the 2 minute mark right here. So we can follow this over and see that. So Jessica would win if it was a distance of half a mile for the entire race. And so at approximately what point would Jessica and Carl be tied? So let's look back at the graph to answer that question. Okay, so this question is asking about this intersection point. And so this intersection point is the point where their distance is the same. They have traveled to the same 1 mile mark of the race. And so here it is. And so we could say that 1 mile into the race, they were tied, and that happened at 4 minutes. So 4 minutes in, they were both at a mile. And then if they continued at their constant rates, Carl would keep pulling away, and Jessica would fall further behind. Okay, and that was a system of linear equations. Okay, so let's look at our lesson summary. Simultaneous linear equations, or a system of linear equations, is when 2 or more linear equations are involved in the same problem. Simultaneous linear equations are always graphed on the same coordinate plane. The solution to a system of linear equations is the set of all points that make the equation of the system true. If given 2 equations in the system, the solution must make both equations true. And that's what we were finding here, is that to make both of them true is a little bit harder than finding points where one equation is true. And then the notation that we use for a system of equations is to list the equations and put the brackets out front. Okay, so good luck with the exit ticket and the problem set on this. If you need help, again, once you've taxed your brain, go to the answer key and check to make sure you're on the right track. Okay, I'll see you back here for lesson 25.